My name is Ali Begen. I am from Ozyegin University in Istanbul, Turkey. Um, Today, I'm going to talk about MOQ, which stands for Media Over QUIC. And I will be describing some of its features. I'm not really trying to sell you anything, but I would like to explain what MOQ can do and what we expect it to do over time. We are also part of OpenMOQ, Eco-Industry Consortium. You probably have heard of this. It is quite new. The idea behind OpenMOQ is to develop MOQ software that will scale really well for CDNs and so on. So they are really trying to build MOQ at scale. All right, let's start. First of all, there are a lot of people. By the way, there was another slide, but the host asked me to replace this slide with something less offensive. Uh, um, so I started working on adaptive streaming in my PhD. So that dates back 2001, and while I spent around 10 years at Cisco, also working on these systems, and I've been part of Dash since day one as well. I'm one of the editors for the spec and one of the co-chairs for the subgroup. Anyway, so we developed Dash, and then at the same time, Apple developed HLS. We developed low latency Dash, and then low latency HLS came out, and so on. And then there are technologies, non-open technologies like Psi that people keep using, right? And the ultimate goal is really reducing the latency, improving the scalability, achieving synchronized playback, and so on, right? So they all serve a purpose, but today I am trying to convince you, again, I'm not really trying to sell you anything, MOQ is going to do a much better job in terms of all these things. So let's continue. So first of all, I always try to start with this slide just to set the stage so that you can understand what this QUIC protocol, which is an RFC, which has been deployed pretty much on every browser and so on, can do, right? QUIC is a multi-lane highway. It's a transport protocol that's meant to replace TCP. So over this multi-lane, you can transmit multiple things at the same time. And they can be transmitted independently and in different prioritized fashion. So if you are the sender, the protocol is running in the user space. The congestion control, rate control is all up to you, right? So retransmission machinery can be optimized for your application. And then here there are multiple streams like high priority, medium, and low priority. You can prioritize them as you like. So if this video conferencing call, audio is going to be the top priority, slides are going to be medium priority, and video is going to be the least priority. Meaning that the audio is going to make it to the other side most of the time. And then if there is bandwidth, slides are going to make it. And then there is further bandwidth remaining, then video is going to make it. So you don't want to jeopardize your audio while you are sharing your slides. And everything happens in a single QUIC connection, but there are multiple streams. Now, there is no in-order delivery guarantee between different streams because they are at different priorities, but each stream has that guarantee. So audio packets are going to arrive in order, and video slides packets are going to arrive in order as well. Now, streams can be canceled without hurting the connection itself. This is something we don't have in TCP. TCP is a single stream connection. So if you kill the stream, you kill the TCP, which means you need to reconnect and go through the slow start again. Here, you can open as many streams as you like. And then everything is encrypted in QUIC, end-to-end encrypted. So your ISP cannot really see what you are doing. Your state, your government cannot see what you are doing either, right? If you need some sort of quality of service from the network, you need to open multiple QUIC connections, but then that really defeats the purpose. Now, let's look at MOQ transport. It is an IETF standard that's being developed for the last 4 or 5 years now. And I've been very happy to get involved since day one with some of the colleagues here, like Luke, for example. It is, first of all, it is a latency tunable protocol. So unlike many other protocols that we have today, it is latency tunable. So it can deliver real-time data. It can deliver on-demand data. It doesn't really matter. It is cache friendly, so that's very important. And it's a PubSub protocol, unlike a request response type of thing. And it can be used for both ingest and distribution. So you can use it pretty much anywhere in your network. So for example, we have a FIFA World Cup, right? There are all these publishers, and then there are all kinds of subscribers on the other side, all around the world, right? And they are going to get this, the different matches, different audio streams, and so on, by using this PubSub protocol. At the same time, it could be like a Twitch broadcast or another online podcast, real time, and then it will be published. It will go through a bunch of relays, and then it will be delivered in real time. You can also add DVR functionality if you want to. Now, the transmission happens over QUIC or web transport, which is, since the last update for iOS and Mac OS, it is also available in Safari now, so it works pretty much in all browsers. So if you're in a non-browser environment, then QUIC is the way to go. So there are streams going from the publisher to the subscribers, and then there's a bidirectional control stream between the entities, and there are one or more relay points between them, right? Those are your caching points so that you can fan out. And now what we are going to talk about, at least I'm going to show some examples of adaptive and prioritized delivery at each of these individual locations, publishers, relays, and subscribers, what we can do to make delivery work better. So this is a chart I also use in my presentations. This is from a survey paper we published earlier this year. So there are high latency applications, typical latency applications, low latency applications, ultra low latency or near real-time latency, whatever you want to categorize with, right? So we have dash HLS for all this stuff on the left-hand side, right? Dash HLS can achieve 10 seconds very easily. It's not a problem. We have low latency extensions for latency is on par with broadcast TV, so 5 to 7, 8 seconds. And now we have WebRTC, right? It has been around for a longer time, and that's for near real-time latency applications or ultra low latency applications. But then, there was this small gap between around 1 second area where low latency dash or HLS couldn't achieve, and WebRTC wouldn't actually go up there, right? So initially, this was the goal for media over QUIC transport. So we wanted to address the 1 second latency barrier. Now, WebRTC has all these complications, which you may or you might not agree with. It is, since there's no relay infrastructure unnecessary, it's not mandatory. You need to have peer-to-peer sessions establishments. It's not latency tunable. It's always real time. It is not cacheable. There's no WebRTC CDN. So it's very limited set of codecs. You cannot really use the fancy features of new codecs and so on. And, a bunch of other things. Obviously, you can override the WebRTC spec and start supporting some of these, but then it's not going to be WebRTC anymore. So we started with this little goal in mind, but then we realized that media over QUIC transport can actually do pretty much everything dash HLS and WebRTC can do. So when we look at the modern media transport, we would like to have tunable latency. That's very important, right? We want to support both on-demand and real-time and anything in between. Adaptive and prioritized delivery. This could be receiver side or standard side or selective discard policies as relay points. And then synchronicity. Well, we would like to have synchronized playback. And scalability, obviously, we would like to have scalability as good as dash HLS. This is one of the first demos we implemented last year for IBC. This was in partnership with Cinemedia, Akamai, and Sixth Floor. So we have real-time basketball game that goes in real-time AI event detection. It captures the events like 1-point shot, 2-point shot, and so on. And then everything goes through our publisher. We have a relay, and then we have a player. All these things are developed by my students. And what we are trying to show is that by using this timeline track, which is based on these events, actually can allow you to do low latency playback with DVR functionality. So over here, we can achieve as low as a few hundreds of milliseconds latency, and we can fetch past points of interest, 16 streams in parallel. There's also prioritization. Live transmission gets the highest priority over fetched streams. Looking at another example, the need for track switching, which is ABR. Track switching is for ABR. So we have a live source here, encoding publisher, relay, and the player. What's happening here is that on the client side, we might have ABR-related reasons and non-ABR-related reasons for track switching. So you might do HD to 4K, 4K to SD transition based on a number of reasons. On the other side, the relay can do switching automatically without asking the receiver, right? It can also do for ABR purposes and for also non-ABR purposes. But the problem is that the relay doesn't know the conditions on the player side, and the player doesn't know what's available on the relay side. So the relay wants to do a lot of things, in terms of rate adaptation and so on. But if you don't know the conditions on the player side, that's not going to really work very well. And same thing, if the player doesn't know which tracks are available on the relay side, the switching may not really work very well. So desired features of track switching, seamless track switching. First of all, we don't want to have any stall when we are track switching. That's very important. And we don't want to have any gaps or skips, especially if there's a penalty and then you miss it, and then it's a goal. Obviously, you don't want to see that. And then we want to minimize the waste. So when you're doing track switching, so these are MOQ groups. If you switch from one track to another, you don't want to overlap the tracks so that the waste can be minimized. We have a tough goal to achieve less than a second ABR with MOQ. So this is something we can do today with Dash using L3D extensions, as you know, and same thing can be expected from MOQ as well. So remember, ABR can only happen at the group boundaries or keyframe boundaries, right? And we would like to have keyframe durations multiple seconds, but we would like to have ABR in less than a second. So how we are going to do this? Well, we are going to have multivariant encoding, and we are going to pack different versions of the same content in a single track. And the relay is going to receive them, like in the same track, we have a 6-second COP version, 2-second COP version, and half a second COP version. And then the relay is going to have some sort of extension, extra logic that will interpret the client request and then send what is necessary. So this is something we implemented, and we only need this few values for our extension, and the relay is going to look at these values and do the right transition for you. Here's an example. So we have a 6-second variant, 2-second GOP variant, and half a second GOP variant. So if you switch in the middle of this group, this is group N, so group N plus 1 is going to come next. So there are all these objects in this track. So if you go this, in the next, as soon as possible, we are going to join the more frequent keyframe track. You are going to get this information, and then you're going to jump to the next higher quality one. And at the end of the boundary, you are likely going to jump to the highest quality one. Since the bit rate is the same, but the frequency of iframes changes, the quality is going to be changing from one track to another. So this is a very similar idea that we have for L3D, and same thing can be implemented in MOQ without any issues. Another implementation we have for MOQ, and this is something under discussion in the IETF, is sender side, which is relay or the publisher, depending on what you are referring to. And it's going to work like this. So the subscriber is going to say, hey, look, I am interested in these 3 tracks, SD, HD, and 4K. I don't want any other resolution, for example, right? So the sender, the relay in this case, is going to subscribe to all these tracks. So they are available on the relay side, on the caching side. And then it's going to look at the real-time bandwidth values. depending on what kind of bandwidth it thinks the client has, it's going to pick those one of those tracks. Maybe track 1, maybe track 2, maybe track 3. And then at each group boundary, it's going to repeat the same thing, right? Now we have an improvement on top of this. The client might also say, my latency budget is, let's say, 200 milliseconds, right? The server, the relay in this case, is going to look at that requirement. And if a subgroup that the live media that you are sending is not going to make it within this time budget, it's going to be discarded without harming the QUIC connection. And then you're going to continue with the next QUIC stream. Now, looking at the real-time bandwidth sometimes is quite difficult because it is very noisy data. So there are other things that we can look into. For example, the number of active streams, so that we can understand whether there is congestion in the network or there is no congestion, and then we can try upshifting. That's about the ABR part, and I want to show a couple of slides on the synchronized playback. This is an experiment we did between Istanbul and Vancouver, so it's a pretty long round trip time, about 300 milliseconds, and we have a relay in Frankfurt, Germany, okay? And we would like to watch something together, which is synchronized playback. It could be on-demand video, or it could be live video. Research has shown that if the latency difference between different viewers when you are doing synchronized playback is less than 200 milliseconds, like 6, 7, 8, 10 frames, it's usually okay. People don't really mind the latency difference. If it is less than half a second, it is acceptable. If it is more than half a second, then you start spoiling the game or the video, right? So this is our range. That's where we would like to keep the latency difference. We don't need frame accurate synchronized playback, but we want to have at least half a second latency difference between multiple participants that are watching the same content at the same time. So normally, this watch party concept is today done by using WebRTC for the video conferencing part, where people are chatting and sharing their emotions, and the streaming part is done by the HHLS. We don't want to do this, dual stack approach. We rather want to use a single stack, MOQ stack, and then we are going to be hopefully achieving a better performance, because these two different things will be sharing the same resources for different purposes. The relay is going to be a common to both purposes, right? For both media transmission as well as video conferencing session when you are doing watch party. And the most important thing here is in the middle, shared quiz session, meaning that everything that goes through the relay, whether it is the football game you are watching, or the golf game you are watching, or the video feed coming from your friend, they are going to be all using the same QUIC connection, which means they can be prioritized accordingly. I'm going to show you an example. So this is where our main content comes from. It could be on demand, or it could be live video. And then we have our relay. And by the way, they don't have to speak to the same relay, but this is just for illustration purposes. And there are all these guys who are joining the party, right? We are getting the main content from the publisher here, but then each of these people are publishing their own video camera feeds as well as audio tracks. Now, what we have here is the dual pipe transport strategy. So out of a single QUIC connection, we have a single QUIC connection regardless of the number of partiers in the room, right? So we have a control stream. Obviously, that's the highest priority. And then we have the context pipe, which is carrying our main content. The football game, for example. There could be audio track, video track, timeline track, and all kinds of different tracks for that context pipe. And we use QUIC streams, MOQ streams for this context pipe. Why? Because video is encoded by using differential encoding, and a frame is not really useful if the previous frames have not been received, right? So we want reliability, but we can also discard things if they're going to be too late. Next, it is our excitement pipe, which is coming from each partier. So if there are 5 guys in the party, then I will have that kind of pipe for each of them, like 4 in total. In this pipe, audio is going to be transmitted in QUIC datagrams, We don't need retransmissions for audio packets, and there is no need to recover them if there is loss, right? Video is still transmitted using quick streams, but with an early discard policy. So the emotion coming from my friend is only useful at that time. It's not going to be really useful 5 seconds later, right? So we don't want to really have late video in this case. So this is one of the most important features of MOQ transport, the prioritization. Here is how we are using this in this application. So here is my relay. The content is coming from the publisher. And we have control stream, highest priority. Main content, the football game, is next highest priority. And then from each part here, we are getting an audio and we are getting video. Audio is medium priority. Why? I would like to hear my friends before I see them. And audio is latency critical. It needs to be transmitted in real time, but it doesn't have to be reliably transmitted. If there's packet loss, there's packet loss. I don't really care about it. On the other side, when I am watching my friend's video, it is low priority. It is the lowest priority that I can assign. It is still latency sensitive, but it is cancelable. So if my bandwidth doesn't allow to see all of my friends at the same time, I'm going to start dropping some of them. Okay, so if there is less bandwidth that I cannot support everything, I'm going to continue with the audio only. If there is even less, much less bandwidth, then I'm going to go with only the control, the context pipe, and skip the party video altogether. All right, so I would like to, show all these demos to you. They are all available on the website. If you go to MOQtail.dev, we have the source code, the papers, the presentations, and documentation for each of these projects. They work in different versions of the draft. Just last week, we upgraded to version 18, which is, the current draft in the IETF is version 19, but it just came out a few weeks ago. So we are pretty up to date. But these projects have different versions, as you can see, draft 11, draft 14, draft 16, and so on. And you can play with the code yourself. We are open and welcome your suggestions and contributions. And you can also refer some further slides for each of these topics in more detail, if you would like to. That's about it. And then I hope this was a quick summary of what MOQ can offer to you, how you can use it in practice, and whether the market adoption is going to take place or not, that's TBD, but we are working on it. Thank you.